Okay, so welcome back to this next video in which we are discussing the adrenoreceptors. Okay, so we now want to see how the beta-gamma complex is going to inhibit voltage-gated calcium channels. Okay, and I just for this want to discuss the structure of a voltage-gated calcium channel in a bit more detail, and I think I'll go and start a new piece of paper because it would be nice to have everything in one place rather than having to switch another piece of paper and leave one drawing behind at the bottom there. Okay, so let's do then voltage-gated calcium channels. Okay, and voltage-gated calcium channels are often abbreviated to VGCCs for short. That's what we abbreviated them to previously, but it is short for voltage-gated calcium channel, VGCC. Right, okay, so let's see the structure of these voltage-gated calcium channels. Now, basically, they're quite big structures. They have a lot of separate subunits. Okay, so let's have the plasma membrane here. Okay, and now I'll start with the main subunit, which is a subunit known as the alpha-1 subunit. And this is the subunit that actually has the pore going through it, which allows calcium to move across the membrane. Okay? So this is the alpha-1 subunit. Now this is actually all one protein, okay? So it really is one protein, so it's not a tetramer as you might expect, since we've seen a lot of tetramers now. It is one protein that makes the entire pore of the voltage-gated calcium channel. Okay, but then attached to this alpha-1 subunit you have a number of accessory subunits. Now these are called accessory subunits for a good reason, and that's because they're not actually necessary to get a functional voltage-gated calcium channel. Okay, so the alpha-1 subunit is the only absolutely necessary subunit to have in a voltage-gated calcium channel. All of the subunits that I'm about to tell you about are accessory to the alpha-1 subunit. Okay, so let's see these accessory subunits then. So, sitting alongside the alpha-1 subunit here, we have a subunit that's called the gamma subunit. Okay, and we'll come back to that in a moment. Attached to the intracellular aspect of the alpha-1 subunit, we have a subunit called the beta subunit. And then finally, another subunit that's attached over here to the alpha-1 subunit is what's known as the alpha-2 delta subunit, which is made out of the alpha-2 portion, which is extracellularly, and then this delta portion, which has a single membrane-spanning alpha helix, and which is attached to the alpha-2 portion by disulfide links. So this is called the alpha-2 delta portion. Now you might wonder, well, why is that considered a subunit together? Why aren't alpha-2 and delta separate subunits? Well, the reason is that they're actually produced by the same gene. So you have a gene which will be transcribed into a piece of mRNA. That mRNA will go through a ribosome and produce you a massive great polypeptide, and basically that polypeptide is cleaved into two portions: the portion which will make the alpha-2 protein subunit and the portion which will make the delta portion, and then they join back together in a different way, not this time by peptide links but by disulfide links, and that then produces you the alpha-2 delta subunit. So that's why the alpha-2 portion and the delta portion are considered as one subunit, called the alpha-2 delta subunit. Okay, so this is the structure of a voltage-gated calcium channel. Now, what I want to discuss with you is the membrane-spanning topology of the protein that is the alpha-1 subunit. And then I want to show you the structure of alpha-2, delta, gamma, and beta. And I want to discuss with you also the diversity in all of these subunits. Okay, so let's start off with the membrane-spanning topology of the alpha-1 subunit of the voltage-gated calcium channel. Now, this is a massive great protein. So you start off with the amino terminus on the cytoplasmic side of the membrane. Then you have your first membrane-spanning alpha helix, your second membrane-spanning alpha helix, third, fourth, fifth, the P-loop, then the sixth membrane-spanning alpha helix, then a loop in between the 6th membrane spanning alpha helix, and then you have another membrane spanning alpha helix. Now, basically, you're going to repeat this entire structure again. Okay, so I'm going to repeat this structure again. So here's the 4th, the 5th, the P loop, the 6th membrane spanning alpha helix. Then we'll have another loop, and then I'm going to repeat this structure again. Okay, so again, here's this structure repeated, and then I'm going to repeat it one final time. Okay, like so. So 5 membrane spanning alpha helices, a P loop, and then the 6th membrane spanning alpha helix, and then the carboxylic acid tail. Okay, so these 6 regions that are basically repeats of one another, they are called domain 1, domain 2, domain 3. Sorry, these 4 regions that are basically repeats of one another, and then finally domain 4. Okay, and now all of these membrane spanning alpha helices are labeled basically. So the first membrane spanning alpha helix is called S1. The second membrane spanning alpha helix is called S2. The third membrane spanning alpha helix is called S3. The fourth membrane spanning alpha helix is called S4. The fifth membrane spanning alpha helix is called S5. Then you have this P loop in here, which is this loop that doesn't quite make it through the membrane. Then you have this 6th membrane spanning alpha helix, which is called S6. So, if you want to name any one of these membrane spanning alpha helices, let's say we want to name this one here, you'd say it's the S4 because it's the 4th membrane spanning alpha helix, and then you'd say of domain 3, so you'd tell me which domain it's in, and then you'd label it either S1 to S6 or the P loop, basically. Okay, right. So that's the structure of the alpha-1 subunit of a voltage-gated calcium channel. And basically these 4 domains all wrap around into a ring, okay? So it will be like so. So you'll have them wrapped around in a ring, like so. So I'll put this here. This one here will be domain 1. This one back here will be domain 2. This one then domain 3. And then this one over here, domain 4. Okay, like so. So they'll go round like that. They'll wrap around to produce the pore down the middle. Okay, right. Now, it would be beautifully simple if there was just one alpha-1 subunit of voltage-gated calcium channels. Of course there isn't. There are actually 10 different alpha-1 subunits, 10 different genes which produce 10 different alpha-1 subunits. Okay, and they do have different properties, so it's important to know about the different alpha-1 subunits. So, basically, and I shouldn't be writing it there, but we'll get away with it, 10 genes, because I need to draw more on this picture in a moment. Okay, so you have 10 genes, and basically you split them into 3 families. So there is the CAV1 family, there is the CAV2 family, there is the CAV3 family. So this stands for voltage-gated calcium channel 1 family, voltage-gated calcium channel 2 family, voltage-gated calcium channel 3 family. Okay, now, within each of these families you have many genes. So within the first family, for instance, you have 4 genes called CAV1.1, CAV1.2, CAV1.3, and then finally also CAV1.4. Okay, so those are the 4 genes within the CAV1 family, and all of them code for alpha-1 subunits. So the CAV1.1 gene codes for the CAV1.1 subunit. The CAV1.2 gene codes for the CAV1.2 alpha subunit. Okay, right. Then the CAV2 family, we have the CAV... Actually, let me just finish talking about the CAV1 family. So basically, if you make a voltage-gated calcium channel out of the CAV1 family members, okay, i.e. if you use one of these 4 genes to code for your alpha-1 subunit of your voltage-gated calcium channel, then the voltage-gated calcium channel that you produce is called an L-type voltage-gated calcium channel, okay? So, that is what people mean when they say they're dealing with an L-type voltage-gated calcium channel. They mean that the alpha-1 subunit of the voltage-gated calcium channel is one of these 4 genes, basically. Okay, let's now talk about the CAV2 family. So the CAV2 family contains 3 members. It contains CAV2.1, CAV 2.2, and then also that's fine, CAV 2.3. Okay, so if you use the CAV 2.1 gene to make your voltage-gated calcium channel, then your voltage-gated calcium channel will be called a PQ-type voltage-gated calcium channel. Okay? If you use CAV 2.2 as the alpha-1 subunit of your voltage-gated calcium channel, then your voltage-gated calcium channel will be called N-type. Okay? And finally, if you use CAV 2.3 as your alpha-1 subunit of your voltage-gated calcium channel, then it will be called R-type. It will be an R-type voltage-gated calcium channel. Okay? Now, let's move on to the CAV3 family. In the CAV3 family, you have 3 genes. You have the CAV 3.1, CAV 3.2, and then also the CAV 3.3. Okay, and if you make a voltage-gated calcium channel out of any one of these 3 alpha-1 subunits, then your voltage-gated calcium channel is called a T-type voltage-gated calcium channel. Okay, so that's what the difference between L-type, T-type, PQ-type, N-type, and R-type voltage-gated calcium channels is. All it tells you is it gives you clues in some cases, or it tells you exactly in the cases of the CAV 2.1, CAV 2.2, and CAV 2.3 which alpha-1 subunit you are using as your alpha-1 subunit of your voltage-gated calcium channel. Okay, right. So it's not just the alpha-1 subunit that has multiple genes coding for it. The beta subunit and the gamma subunit and the alpha-2 delta also have different genes that code for them. So let's now have a look at the beta subunit. So the beta subunit binds to this loop between domain 1 and domain 2, and it has within its structure 4 alpha helices. Now they are not membrane spanning alpha helices, but they're still alpha helices. Okay, so here's the amino terminus, here's the carboxylic acid terminus, and basically it binds to the loop between domain 1 and domain 2. Okay, now there are actually 4 different genes for beta subunits, okay, and these are called nice simple names. So the 4 genes for the beta subunits are just called beta 1, beta 2, beta 3, and beta 4. So you have beta 1, beta 2, beta 3, and then also beta 4. So those are the 4 genes that code for beta subunits of voltage-gated calcium channels. Okay, right. So not only do you have a choice of which alpha-1 subunit you're going to use if you're going to build a voltage-gated calcium channel, but you also have a choice of which beta subunit you're going to use. Okay, let's now move on to the alpha-2 delta subunit. Okay, so this also has variation within it. There are actually 3 different genes for alpha-2 delta subunits. So remember that both the alpha-2 and the delta portion of the alpha-2 delta subunit come from the same polypeptide that has just come out of a ribosome. Okay, so they're encoded by the same gene. So there are 3 genes. There is the alpha-2 delta 1, the alpha-2 delta 2, and the alpha-2 delta 3, okay? And these 3 genes will produce slightly different alpha-2 delta subunits, and that can modify the properties of the voltage-gated calcium channel. Finally, the gamma subunit is also variable. Now, the gamma subunit of all of the subunits of voltage-gated calcium channels, the gamma one is the one that we know the least about. Okay, so let me just show you the membrane spanning topology of the gamma subunit then. And the gamma subunit has 4 membrane spanning alpha helices, like so, and its amino terminus and its carboxylic acid terminus are both intracellularly. Okay, now an example of a gamma subunit is the protein stargazing. Okay, and again, these gamma subunits can modify the electrophysiological properties of the alpha-1 subunit. So they can modify the conductance of the channel, they can modify what voltage it's actually going to open at, things like that. Okay, right. So That's the structure then of a voltage-gated calcium channel. So what's actually going to happen is these beta-gamma subunits are going to come and bind to these voltage-gated calcium channels, and they're going to inactivate them. So once the beta-gamma subunit is bound here, basically, even if the membrane becomes depolarized, the voltage-gated calcium channel won't open. Okay, so you're not going to get that calcium coming in upon an action potential actually occurring, and that calcium is what triggers the exocytosis of the synaptic vesicles. So without it, you can't turn an electrical signal on the membrane of the axon terminal into an actual signal that's going to produce exocytosis of the synaptic vesicles. Okay, so basically, this is going to block the release of neurotransmitter by the axon terminals. So through both of these mechanisms, by blocking the action potential actually propagating into the axon terminal, and also by blocking the action potentials that do make it into the axon terminal from actually triggering calcium entry into the cytoplasm, we can stop the release of neurotransmitter from that axon terminal. Okay, and this is how these alpha-2 receptors are going to block the release of noradrenaline from noradrenergic nerve endings. Okay, so the last thing I just want to discuss are agonists and antagonists for the alpha-2 adrenergic receptor. Okay, here we go. So here's the receptor. Here's the amino terminus of the receptor. Here's the carboxylic acid terminus. So we know that noradrenaline and adrenaline are both endogenous agonists for the alpha-2 adrenergic receptor. And in the case of the alpha-2 adrenergic receptor, adrenaline has the greater affinity than noradrenaline. Okay, so adrenaline has a slightly greater affinity than noradrenaline. However, we want to know about some exogenous drugs that we can use to affect these receptors. Okay, so the best example of an exogenous agonist of alpha-2 receptors is clonidine. Okay, so clonidine will bind to the alpha-2 receptors and activate them. Okay, and when you do that, what happens is the noradrenergic neurons will be inhibited from releasing noradrenaline, so you're going to get lower release of noradrenaline, basically. Okay, and clonidine is actually used as an antihypertensive because of this function. So remember, adrenaline being released onto the smooth muscle that surrounds the blood vessels actually causes contraction of those smooth muscles. Okay, so if we block the release of adrenaline, if we block the release of noradrenaline from neurons onto those smooth muscle cells by presynaptically inhibiting those neurons, then we're going to stop the release of noradrenaline onto those smooth muscle cells, and hence we will hopefully reduce the contraction of those smooth muscle cells and reduce blood pressure. In addition, clonidine also acts centrally, basically. It acts on the level of the brain as well, and actually reduces sympathetic outflow. So it can also actually end up reducing the release of adrenaline by the adrenal glands. Okay, so there's an agonist for the alpha-2 adrenoreceptor. Antagonists then for alpha-2 adrenergic receptors. A good example of an antagonist for an alpha-2 adrenoreceptor is yohimbine. Okay, so yohimbine. Okay. Another example of an antagonist for an alpha-2 adrenergic receptor is idazoxan. Okay, so idazoxan. And basically, these two drugs, yohimbine and idazoxan, will bind to the alpha-2 adrenoreceptor, and they won't stimulate the alpha-2 adrenoreceptor, but they will stop adrenaline or noradrenaline from being able to bind there. So they will stop activating ligands, agonists, from being able to bind, and hence they will block the activation of the alpha-2 adrenoreceptor. And idazoxan is being investigated for its antidepressant function. Okay, basically the idea is in depression you have too low levels of two major two major neurotransmitters, serotonin and also noradrenaline. Okay, so if you could block the auto-inhibitory negative feedback onto the neurons which release noradrenaline. So let me just draw a picture of this. Okay, so let's say this is a neuron in the brain that releases noradrenaline, and in depression the noradrenaline levels are too low. Okay, basically the idea is that if you could block these presynaptic receptors here that inhibit the release of noradrenaline, okay, so if you could block these, then they'd release more noradrenaline, and then the noradrenaline levels would go up. Okay, so those are two antagonists of alpha-2 adrenoreceptors.